Hello, I'm Paul Campbell. Welcome to my channel. I'm continuing my talk on gamma. Now, in part 1, I explored the origins of the use of gamma in photography. That went back to 1890. Today, I want to follow through the meaning of gamma in analog television, digital television, and modern photography and video. But before I go on, I want to recap something about the characteristic curve for film. Now, this is a graph of density against the logarithm of exposure, and it looks like this. We plot density on this axis, and on this axis we plot the logarithm of exposure. Now, we use the logarithm of exposure because exposure gets very, very big. It doesn't proceed linearly like 1, 2, 3. It proceeds doubling every time, like 2, 4, 8, 16, just like we do with the shutter speed on the camera. And the characteristic curve for film looks something like this. We have a straight part, we have a shoulder, and of course we have a toe. Now, the usable part is the straight part, which runs from there up to there. And that gives us a usable range of exposure between those 2 points. Now, if you recall, this straight part has a slope, and that slope is what we call gamma. Now, I want to change the presentation of this just a little bit, because, you see, density is actually equal to the logarithm of opacity. And we use density instead of opacity because, like exposure, opacity gets very, very big very quickly. But if we're using density, we're actually disguising the fact that this is a log scale. So I'm going to change this. I'm going to remove density, and now we're graphing log opacity on this scale and log exposure on that one. Now, why am I doing that? Well, there's a bit of mathematics involved here. You see, let's get rid of the parts we don't use. And what we've got then is basically a straight line on a log-log graph. And it turns out that if you've got a straight line on a log-log graph, then you have a mathematical relationship between the two variables of the form opacity, because that's what we've got here. And we'll call that O. Opacity is equal to exposure to the power of gamma. Now, this is what we call a power function, and it'll become more important later. We didn't do this in the days of film because we weren't interested in the mathematics. The characteristic curve was enough for our purposes. All right, now let's move on. Television actually goes back further than you might expect. It goes back, the concept goes back into the 1800s. Now, that's a long time ago. And the first kind of actual practical television was what's called mechanical television, where there's a spinning disc with holes in it that was used to scan an image. Now, that gave way to fully electronic television, where the image was scanned by an electron beam. Electronic television was first successfully demonstrated in San Francisco in 1927. Now, before that, in 1925 in London, John Logie Baird, the Scottish inventor, made the first ever public display of working mechanical television. But I'm going to move forward to just after the Second World War, when commercial electronic television was coming into its heyday. Television cameras at this time used electron beam technology, as did the television receivers. Television cameras were based on electron beam tubes, such as the Orthicon, the Vidicon, and later the Plumbicon tubes. I used a scanning electron beam to read an image projected onto a semiconductor material. These tubes were quite compact, surprisingly small for such ingenious devices. Color cameras used 3 or even 4 tubes. Television receivers used cathode ray tubes, or CRTs. In the CRT, a scanning electron beam again is used, but this time to draw an image on a phosphorescent screen. The receivers, the CRTs, the television receivers, are much larger than the camera tubes because, of course, we want to be able to see a large image. Now, let's take a look at the characteristic curve for the camera tubes. This is the curve for a Vidicon camera tube. Now, on this axis, we have the logarithm of the output current, which we'll call I.O., and on this, the horizontal axis, we're going to have the log of luminous flux, which is just the amount of light falling on the photosensitive area. Basically, it's the same as what we called exposure on the graph for film. Now, unlike the curve for film, this curve for the Vidicon tube is essentially a straight line. But just as for film, the slope of this line is called gamma. Now, if we plot two variables on a log plot like this, and we get a straight line, then mathematics tells us that the relationship between the variables is a power function, with the power equal to the slope of the line. In this case, that means that I is equal to L to the power of gamma. Now, we should actually put a constant in there, but I'm going to leave it like this just for the sake of simplicity. Now, if we graph that relationship using linear axes instead of logarithmic, that graph of I against luminous flux is going to have one of these forms, depending on the value of gamma. Now, this curve is for a gamma that's greater than 1, for instance. This one has gamma equals 2. And if gamma is less than 1, the graph is going to look like this, for instance. This one has gamma equals 0.5. Now, gamma equals 1 is a special case, because if gamma is equal to 1, then I will be equal to L to the power of 1, and L to the power of 1 is just L. So that's going to be I equals L, which is a straight line. If we have a system that takes an input and changes it into something else according to some mathematical function, then we call that function the transfer function for that device or system. Now, these camera tubes take luminous flux as an input and they change it into a current according to the formula I equals L to the power of gamma. And this function, I equals L to the power of gamma, is called the Opto electronic transfer function for these tubes. Now, for short, we call that the O for opto, E for electronic, T for transfer, and F for function. That is the OETF function for short. Now, I'll mention something about the output here. It's shown as a current, but the current from the tube will flow through a load resistor, and that will cause a voltage to show across the resistor. Now, we could use the voltage as the output because it will be representative of the current, but the current comes first, so that's what we're using in these curves. Now, the voltage in any case will be amplified in the camera electronics. In general, camera imaging tubes have gammas less than 1. The Vidicon tube, for instance, has a gamma of about 0.5, whereas the Vidicon tube gamma is close to 1 at about 0.8 or 0.9. Now, this chart shows the characteristic curves for several imaging tube types. Now, the receiving device, the CRT, television receiver. It also has a transfer function, but this one's called the EOTF. That's the electro-optical transfer function, because the television receiver is converting an electronic signal into an optical or light value. The graph of the transfer function is also called a gamma curve. Now, let's take a look briefly at the television receiver and what's known about its transfer function. I'm going to quote from the Philips Technical Review of 1963. In a picture tube television receiver, the luminance of the screen increases roughly with the square, at least, of the signal voltage applied to the control grid of the tube. In mathematical terms, that is, L is equal to kV to the power of 2. Note that they said at least. In fact, the gamma of TV receivers is around 2.5, so that is L is equal to K times V to the power of 2.5. That's L for the luminance on the screen is equal to some constant times the voltage to the power of 2.5. Now we need to consider system gamma, the end-to-end gamma of the camera receiver system, the OOTF, if you will. Now ideally this should be close to 1. That is, the contrast on the output should be the same as the contrast in the original scene. Now in practice, television is viewed in a darkened room, causing something called the dim surround effect. It causes the image contrast to appear lower than it actually is. So it was decided by those who set standards that the overall gamma should be 1.2 or thereabouts. Now if the receiver gamma is 2.5 and the overall gamma needs to be 1.2, then the camera gamma should be 0.48. The original NTSC specification for analog TV set the camera gamma to 0.45. So within the cameras, a gamma correction circuit adjusted the output gamma to this value. As an aside, slides are usually viewed in total darkness, and the gamma of slides is consequently designed to be 1.5. That is very contrasty. Then they look normal in the dark surrounds. The same is probably true for cinema film. So there we have gamma for the analog television system. The camera with gamma equals 0.5. The gamma correction circuit, which adjusts the camera output gamma to 0.45, and a television receiver with gamma equals 2.5. The overall end-to-end gamma of 1.125 with that arrangement. Now, along comes digital. Now, at first, only the camera is digital, using CCD, charge coupled device technology. This was developed around 1969, but it took a few years before it was integrated into video production. Now, like the Plumbicon, the CCD camera has a gamma of approximately 1. So the gamma correction being applied is the full 0.45. But now the camera is digital, not analog, and the output is in the form of digital numbers. Now digital numbers are integers, and there is a fixed limit to how many integers are available in any digital number system. For 8-digit numbers, are you serious? For 8-bit numbers, there are only 256 possible values. Now, in fact, only about 220 of those are used. Now, it turns out that there is some serendipity here in the application of gamma correction. Each pixel in the CCD converts photons into electrons. Periodically, the pixels are read out. They have a voltage proportional to the number of electrons. And this voltage is converted into a digital number using at least a 10-bit system. In later cameras, it's a 12 or a 14-bit system. This high precision supports the processing that takes place to create the image. After processing, the signal is converted down to the number of bits used for broadcast or other output. Now, it turns out that if the gamma correction is applied after this final conversion, at least 11 bits are required to avoid banding in the dark areas of the image. But if the gamma correction is applied before the final conversion, only 9 bits are required. And for TV, 8 bits are adequate. Now this ties in with the human perception of brightness, which, like the electron beam-based camera tube, follows a power law. Recommendations for television and video set a gamma correction of 0.45 as a standard in Rec 601 and later Rec 729. In application, it's a little different though, again because of mathematics. If a pure power function is used, it causes difficulty close to zero in the deeper dark tones, getting close to division by zero problems in calculations. So the actual Rec 601 function is a hybrid of a straight line close to zero and a power function after that, as you can see here in the specification. Now this turns out to have an overall gamma close to a pure power function of around 0.5. Now note that the 0.45 gamma function existed before digital came along. If it hadn't existed, it would have been necessary to invent it. It's truly one of the great coincidences of modern technology. Now, looking back, gamma was originally the Greek letter used to designate the slope of a film's characteristic curve, and it came to mean the contrast of the film. As time and technology have passed, the meaning of gamma has changed. It's now taken to mean the transfer function of an imaging device. It still means contrast, though. Digital still cameras, inherited the Rec 601-729 gamma function. In the early days, they were all 8-bit devices. That is, the output was 8-bit. Internal processing used 10 or more bits. Now, 8 bits was just adequate for most purposes. You know, even the fairly recent Sony A7 III is still a nitbit camera. Are you serious? The A7 III is still an 8-bit camera, but it works perfectly well. Manufacturers, however, have made some modifications to the Rec 729 gamma curve, adding a knee to it to get better roll-off in the highlights, like this, and changing it completely. Canon's wide DR uses a more radical modification of the curve, seen here. And then we have log profiles, which have gammas completely incompatible with most output devices, that is, displays. And they need to have a gamma correction applied manually in software to make their output usable. Now, all of this is beyond the scope of the present video, and I may address it in the future. In the meantime, if you found anything interesting here, please take the time to subscribe. Until next time then, goodbye, and may your God go with you.